In the last video, we began looking at this spring mass system where we have two masses and three springs. And we used Newton's second law applied to free body diagrams for those two masses to obtain the governing equations. And they were the second order ordinary differential equations mx1 double dot is equal to minus 3kx1 plus kx2, and 2mx2 double dot is equal to kx1 minus 2kx2. We then obtain the natural frequencies of vibration for this system. Again, those are the frequencies for which the entire system is oscillating at those same natural frequencies. And this is what we got. So omega 1 and omega 2, 0.8805 and 1.7958 times the square root of k over m. And remember, we said that when we get the general solution, which is the focus of this video, the general solution is going to be a linear combination or a superposition of these two natural frequencies, and we'll see that in just a moment. As we've been doing throughout this section, we're going to use diagonalization to solve this problem. Now we have two coupled second order equations, so we're going to convert that into four first order equations, 2 times 2. We'll use the substitution u1, u2, u3, u4. u1 is equal to x1, u2 is equal to x2, and then u3 is x1 dot, u4 is x2 dot. This is not unique. We could have said u1 is x1, and then u2 is x1 dot, and u3 is x2, and u4 is x2 dot, for example. That'd be perfectly fine. Obviously, the system we get when it's uncoupled will look a little bit different, but in the end we get the same solution back in terms of the original variable. Then to get the first order system, we simply differentiate these four equations. So when we differentiate the first one, we have u1 dot is equal to x1 dot, but x1 dot, that's just u3 from our substitution. u2 dot is equal to x2 dot, but x2 dot is equal to u4, again from our substitution on the previous slide. And then u3 dot is x1 double dot. x1 double dot we get from the first of the governing equations, which was minus 3 capital Kx1 plus capital Kx2. Here capital K is the spring constant K over the mass m. And again, we want to write this in terms of the new variables u1, u2, u3, u4, not x1, x2, x3, x4. So x1 is u1, x2 is u2. Finally, for the fourth equation, we have u4 dot is equal to x2 double dot, but x2 double dot from the second of our governing equations is a half capital Kx1 minus capital Kx2, where again x1 is u1 and x2 is u2. So in the end, we have four first order ODEs involving u1, 2, 3, and 4. And we can write that in matrix form here. You can see that it's homogeneous. There's no F terms. And so we get a 4 by 4 system of coupled first order equations. You'll notice that this is not a symmetric matrix. It normally is not when we do these sorts of transformation. Let's set capital K is equal to 1 just to keep things simple so we don't have this extra parameter floating around. So because this is a 4 by 4 system, I'm actually going to use Mathematica to get all these solutions that you're going to see, get the eigenvalues, get the eigenvectors, and do all these operations. So I'll give you the results, but don't get bogged down in the details. Focus on the big picture. The big picture, the steps that we're following are exactly the same as in the previous examples that we've done. First, we've taken our two second order equations, converted them into four first order equations. Now we're going to get the eigenvalues, eigenvectors to form the modal matrix. We'll do the diagonalization, and then we'll convert back to the original variable. So this is no different than in the previous examples. It's just more complicated numbers. So if I put this in and I get the eigenvalues, these are the four eigenvalues that I get. The first thing you'll notice is they are imaginary. So they're complex conjugate pairs, plus and minus 1.7958 and plus and minus 0.8805i. The other thing you'll notice is these numbers look familiar. Those are the same as the natural frequencies. And so these numbers are going to carry all the way through the rest of the problem because these are the natural frequencies of the system, and any general motion of this system will be some linear combination of these two natural frequencies. Again, get the eigenvectors using Mathematica or MATLAB, and they are complex, as you might expect, because we have complex eigenvalues. So we can form the modal matrix, and so here's U1, U2, U3, U4. Now remember the road signs. So we have a non-symmetric A, but we have distinct eigenvalues, so the eigenvectors should be and are linearly independent. So our modal matrix U will indeed fully diagonalize our system of equations. And that's done using this transformation from U to V. And in terms of V, the solutions are given here. Once again, as soon as we know the eigenvalues, we know the solution of the uncoupled system in these cases where it's fully diagonalized. So then when we transform back, remember we've actually done two transformations. We've gone from x1, x2, the original physical variables, the locations of the masses. We've converted that to u1, 2, 3, and 4 to put it in a system of first order equations. Then we did a transformation using the modal matrix to get to V, with respect to which the system is uncoupled. We solve it, and then we need to transform back and transform back. So when we solve our system, we get the solutions for U1, U2, U3, U4. Here they are for the V's, and then we just simply multiply by the modal matrix to get it in terms of the U's. But remember, x1, the original x1 is just u1, the original x2 is just u2. So those are actually the only two that we need. We don't need u3 and u4. And here they are. So I've written them in terms of the v's, which we know right here. So I didn't put those in because I wouldn't be able to fit them on the slide. Notice the coefficients. You got these imaginary numbers in here and so forth. So we're not quite done yet. Normally, this would be the general solution. We would put in the initial conditions and we'd be done. In cases where we get complex eigenvalues and eigenvectors, we need to do this extra step that we illustrated in one of the previous videos of using Euler's formula to extract out the real and imaginary parts and then linearly combine them into a general solution. So let's take a look at how that works. So using Euler's formula, here's the real part of x1, the imaginary part of x1, real part of x2, imaginary part of x2. And again, I've done all this in Mathematica, so you know, to do this on paper would be very tedious. But once again, you see sines and cosines of 0.8805 and 1.7958, which again are these two natural frequencies that we expect. And I've highlighted them all the way through so you can see how they trace through the solution. Once we get the real parts and the imaginary parts, we can then combine them to get a general x1, which is a times the real part of x1 plus b times the imaginary part of x1. Same thing for x2, constant times the real part of x2 plus another constant times the imaginary part of x2, and we get our two solutions. Now you'll notice that everything's real. There's no more i's, no more imaginary numbers anywhere, so everything is real. So this is the solution for x1 and x2. We still have some constants in here, and that's because we haven't introduced the initial conditions yet. You'll notice I did a little sleight of hand with switching things around with the constants. So the little a1 through a4 are really capital A times c1 plus c2 and so forth. So I'm just combining all these constants into a set of 4 constants just to keep things a little bit more manageable. Now the first thing you'll notice, again, I've emphasized this a couple times, but is the superposition of the two natural frequencies. So any set of initial conditions, the solution that we get is going to be some linear combination of these two natural frequencies. So you see the 0.8805, 1.7958 over and over again through the solution. The other thing you'll notice, just like in the previous example that we did, is the oscillatory behavior that you expect to get physically from the spring mass system is consistent with the fact that we end up with these sines and cosines of the natural frequencies, so oscillatory types of behavior. Okay, so let's introduce some initial conditions and see what the solutions look like. We're going to define the positions and the velocities at t is equal to 0 for both of the masses. For the left mass, we will hold it at its original position, its neutral position, x is equal to 0, and we will give it no velocity at t is equal to 0. So position and velocity are 0 at t is equal to 0. The right mass, x2, is going to be shifted over 1 unit, so x2 will be 1, and then held in place so that x2 dot is equal to 0. The initial velocity is 0. And then at t is equal to 0, we hold everything in place. At t is equal to 0, we let it go, and we see how the solution evolves with time. So given these initial conditions, different initial conditions will give different values of these a1, 2, 3, 4 constants. You can think of them as the integration constants. But this particular set will give us this system of equations, 4 by 4 system, that we solve in order to get the constants, a1 through a4. You'll notice the right-hand side vector actually contains these initial conditions. All of this comes from the equations for the system. When we solve that, we get a1 and a4 are 0, a2 and a3 are these constant values. That's the solution for this particular set of initial conditions. If we were to plot this, x1, which is the solid line, so this is x1 right here, and x2, which is the dashed line right here, they evolve in time as follows. So x is up as positive, down as negative. So you can see x2 started at 1. According to our initial conditions, x1 started at 0. And then they oscillate back and forth with time. So once again, the general solution for these particular initial conditions, for which there's nothing particularly special, is a combination of these two natural frequencies. And this is the solution that we get that continues with time. You'll notice there's no damping, there's no friction in the system, so the amplitudes don't decay, this oscillation just goes on forever. So we could ask the question, given our natural frequencies, is there a set of initial conditions that only excites one of the natural frequencies? Let's try omega 1, and indeed that is the case. So there is a set of initial conditions, both positions and velocities, that when we put those in, we will only excite one frequency. So you can see the amplitudes of these curves are different, but the frequencies are the same. The wavelengths and the frequencies are the same. So this is for omega 1. What if we wanted to excite omega 2? Well, we can do a similar thing and determine the appropriate initial conditions. I won't get into how I determine those, but determine the initial conditions such that we only excite the second natural frequency, omega 2. And that's shown here. Again, you can see the amplitudes are different. You can even see that the phases are different because they're going in different directions. However, the frequencies are the same. The wavelengths are the same for both of the masses. All right, so let's make some comments about what we've just seen. First of all, the system that we just looked at is called an autonomous system. Now, of course, this terminology is used in a number of different ways today with autonomous vehicles and autonomous driving. And what it means in a mathematical dynamical systems context is there's no external forcing on the system. So there's no F, essentially. And the coefficient matrix only consists of constants. There's no functions of time in our coefficient matrix. So that's called an autonomous system. If there is such a forcing acting external to the system, we call it a non-autonomous system. One thing you may have wondered in going from a system of 2 second-order equations with 2 degrees of freedom, when we convert that to a system of 4 first-order equations, are we introducing additional modes? Are we introducing additional frequencies? And actually we're not. So you saw how that worked out. We still have those same 2 frequencies, the 0.8805 and 1.7958, propagating all the way through the solution. We have not introduced any additional frequencies. Also, take notice of the diagonalization that we've done here and what it means for this system physically. So we have a physical spring mass system. We solved it mathematically using this diagonalization procedure. And in doing so, we were able to uncouple the equations. Now, what does that suggest physically? What that suggests physically is that in terms of the variables x1 and x2, the motion of these 2 masses and 3 springs are all coupled together. I can't solve for one without the other because they're interdependent, which is what you intuitively would expect for such a system. However, because we can diagonalize the equations and therefore uncouple them, there's a different set of variables, v1, v2, v3, v4, with respect to which the motion of these masses and springs are all uncoupled. Again, it's a little hard to wrap our minds around that because it's obviously an interconnected, interdependent system. But the math is telling us something about the physics here. And so we need to keep that in mind. So these are called the principal coordinates, these coordinates v1, 2, 3, and 4, with respect to which the system is uncoupled. Again, as I've done in a previous video, let me point you ahead to Chapter 5. So in Chapter 5, we're going to look more at dynamical systems, both linear and especially nonlinear. We'll take a look at some of the interesting behaviors that can occur and look at some really interesting examples where those behaviors arise.